Welcome to our tutorial on increasing availability through integrated condition monitoring. My name is Wolfgang Christ. I'm business developer for power distribution systems. With this short tutorial, I would like to present to you new possibilities to increase reliability with condition monitoring. In general, the availability of electrical protection and switching devices is at a high level. These devices usually operate for 20, 30 or 40 years without any problems. Nevertheless, I do raise the question, why is high availability becoming more and more important? Major industry and trade associations published amazing reports. These reports show challenges in terms of availability of electrical equipment. Here are some examples from industry, infrastructure, medical facilities and data center. The Association of the Industrial Energy and Power Industry reported that 60% of all industrial companies had at least one power outage in the last 5 years. Let's have a look at shopping malls or public buildings. Here, the prevention of a 1-hour power outage in a shopping center saves on average $95,000. Regarding medical facilities, healthcare facilities today has estimated that 23% of conventional backup systems fail when called upon a power outage. As well as challenges in data centers, where the average cost per minute downtime is $9,000. In addition, more than 10% of the outages have cost more than $1 million. Nowadays, a high availability is only considered as of 99.9% or more. For the operation of data centers, an availability of 99.99% is not good enough. Let me go for a data center example with average downtime costs of $9,000 per minute. If the availability is increased by 0.095% from 99.9 to 99.995%, the statistical downtime will be reduced by almost 8.3 hours per year. This reduction will lead to a downtime cost reduction of round about $4.5 million per year. The availability of the electrical equipment influences the amount of the respective downtime or failure cost. The graph shows a simplified low-voltage power distribution with partial redundancy. There are 2 feed-in points in the upper part of the picture, each supplied by a power transformer. The feeder units in the purple circle serve the safety power supply beneath. At this point, the safety power supply is redundant. In the low-voltage main distribution, the failure of one of the violet-marked outgoing feeders can be compensated via the coupling switch in the blue triangle. In case of a failure, the redundant feeder takes over the safety power supply. It becomes problematic when another feeder or protection device fails below the redundancy circuit. If the device in the red square fails, all consumers below are out of energy supply. Unexpected failures can be efficiently avoided in modern power distribution system by means of condition monitoring. The protection components permanently record specific characteristic values over the entire service life. The limit values, such as green dots of the graphic, can be defined for a reaction. These points represent potential errors that are recorded and reported due to integrated condition monitoring. The notification of a limit value exceedance can be done as warning or alarm message. Maintenance measures can thus be planned before faults or downtimes occur. This schematic graphic shows a low voltage system with 3 levels. ACBs, if operated under the specific ambient conditions, usually do not require maintenance for many years. However, they are subject to an electrical and mechanical service life with regard to the switching cycles. Both long-term and short-term events can cause a lifetime reduction. Therefore, the device temperature, the switching cycle, the number and types of protection trip, besides the condition of the main contacts, are permanently monitored. Due to the design, an MCCB is a black box in terms of condition monitoring. Therefore, the relevant parameters are permanently recorded and the health status of the MCCB is evaluated by means of an algorithm. The status of the MCCB is visualized via the local display, by the way, as well as for the ACB. In addition, the status message is available via software or via Modbus TCP. The situation is similar with communication-capable HRC fuses, which offer excellent protection. Fuses have no aging impact if operated with their operating limits. Therefore, an integrated current and temperature monitoring is the best way to avoid a creeping fuse failure. Even classic modular installation devices constantly monitor current and temperature. They offer optimum protection against changed or unclear load conditions. The study from the US Department of Energy assumes that a timely reference to maintenance by use of condition monitoring lead to 25% lower maintenance cost, a disturbance reduction by up to 75%, 30% lower statistical downtime cost due to timely alarm. In addition, energy monitoring according to ISO 50001 is automatically integrated. Further advantages are the prevention of possible damage to the company's image, a transparent and future-proof energy supply, and who knows what additional value the collected data will have in the future. The integration of condition monitoring leads to a considerable small CapEx increase. The value add of condition monitoring pays off with consideration of the OpEx expenses during operation and lifetime of the power distribution. Further information, such as the white paper, can be found on our website. The white paper also provides the link to a real concrete application example. The application example provides all relevant information for the conception of condition monitoring. My colleagues and me are looking forward to receiving your inquiry.